here, in this example, it follows a random variable x follows an exponential distribution. Here integration is a little bit, do you guys remember that UV formula integration? Integration u v dx.
You're talking about integration by parts?
Yeah, integration by parts.
Yeah.
So integration by parts. So I'm just going to write down the formula. Integration by parts. We'll be using that. So it is basically u integration v dx. I'm assuming that u and v, they are function of x. Okay. So minus integration du over dx, integration v dx, and then the entire thing. So this is the formula. Integration by parts. And we'll be directly using this formula, and I will not go through all this Calc 1 integration procedure. So I'm just going to give you the main idea. So this is just the formula that we will use, integration by parts. Here x, the time x between customer arrivals at a service station has an exponential distribution. And exponential distribution, if you remember, we had exponential distribution solution. X follows an exponential distribution. If you remember the Python module for exponential distribution, it is called exponent. So it is x, and there is only one parameter, lambda. And this lambda is the rate parameter. Rate of arrival. Okay. If I ask you what is the range of random variable x, range s sub x is going to be time x. It is time, so it is going to be greater than 0. So it is going to be, you can say that it is entire real line, but it is positive. Only thing, this notation means that you just take the positive values starting from 0. Okay? Because it is exponential distribution, PDF, probability density function PDF, f sub x, is going to be lambda e to the negative lambda x for x greater than 0, and it is going to be 0 otherwise. So this is the definition of PDF. Now we want to find the mean inter-arrival time. So x is the arrival time, but we want to find the mean inter-arrival time where the random variable x, which is the time, follows exponential distribution. So x here is the time. X denotes time. So number 1, mean. Mean expectation of x, which is we denoted with mu sub x, is basically integration 0 to infinity, and it is basically lambda e to the negative lambda x dx. And this is your PDF. This is your PDF, and because we are finding exponential, we just multiply with x here. So now you bring this lambda out of this integration, you are left with 0 to infinity x e to the negative lambda x dx. So this is your, make this one u, this guy is v. Now you directly apply the integration by parts. So make x u and e to the negative lambda x is your v, and you have the integration limits. I'm going to directly make use of UV formula. So your mean mu sub x is going to be lambda. So just in case some of you are writing, so but integration by parts, so that you know what I'm doing. Integration by parts. If you apply integration by parts, and I wrote the formula already, so you can actually see that it is lambda and then x e to the negative lambda x over negative lambda minus integration e to the negative lambda x over negative lambda dx. So e to the this integration will disappear, and you will be left with negative you will be left with negative one over lambda and then x e to the negative lambda x plus 1 over lambda e to the negative lambda x. And you actually limit the integration from 0 to infinity. If you limit the integration, I'm just going to directly write down the answer. It is going to be 1 over lambda. You do all this derivation, I'm not going to go through all this derivation. It is going to be 1 over lambda. Yeah, I have all this derivation, trust me, in my notes, and it is going to be 1 over lambda. And the variance, variance again is the 2 pages of derivation. So variance of random variable x. I'm going to use the formula, the second moment of x, random variable x minus expectation of x squared. So which is second moment of random variable x minus mu sub x squared, which is second moment of x squared minus 1 over lambda squared. So what you do, it is integration 0 to infinity x squared, which means that it is x squared, and PDF is going to be lambda e to the negative lambda x dx minus 1 over lambda squared. Again, you apply UV formula. Apply UV formula. Integration by parts. By parts. Integration by parts, you go all the way and you will see you will see variance of random variable x that follows exponential distribution. It is going to be 2 over lambda squared minus 1 over lambda squared, and you are left with 1 over lambda squared. So your final answer, variance of x is 1 over lambda squared. So variance of a random variable that follows exponential distribution with parameter lambda is simply 1 over lambda squared. Yeah, at home you may want to just practice calc 1, integration by parts. You will see that it's 2-3 pages of derivations. Yeah, I skipped all those derivations. But I gave you the formula. I just applied the formula. It's just straightforward integration. Next. Yeah. Next, I'm not going to write it down, whatever derivation I had. I typed them and I'm just going to show you. Previously, when x follows Gaussian distribution, I said that if x follows Gaussian distribution with parameter mu and sigma squared, I used to say that these are parameters. Now I'm not going to say these are parameters anymore. So now I can actually prove using the expectation formula, I can actually prove that if you take the expectation and given this PDF, this parameter is actually mean and this parameter is basically variance. And you can actually see, so expectation x, f sub x, x dx, you substitute this PDF with this expression and this x, and you use Gaussian integration. If you use Gaussian integration formula and apply the result, the Gaussian integration is going to be square root over 5. Apply that integration, and then do you guys remember odd function, even function from calculus? Odd function, a function is said to be odd if g of minus u is negative g of u. A function is said to be even function if g of minus u is exactly the same as g of u. So this is even function. So this function is even function, but g of minus u equals minus g of u is your odd function. So you will end up with odd function, and I have all my derivations typed. So eventually you will say that all these guys will disappear, you will be left with just me. So that's why there is a reason where the Gaussian random variable is written as such. There is a reason why Gaussian random variable is written as mu and so on. And you can actually do the same to show that integration variance of x, where x is a Gaussian random variable with parameter mu and sigma, you can actually see that integration negative infinity to positive infinity, you have x minus mu squared and then 1 over sigma square root over 2 pi, e to the negative half x minus mu over sigma squared dx. You will see, if you do this integration, you will end up with sigma squared. This integration, you will end up with sigma squared. It's guaranteed. Okay? So, I skipped all those proof, but in the exam, guys, I will not be asking you to write the proofs. Mainly numerical problems. So now, let's see how to utilize this expectation. So we have an example here. Expected value of a function of a random variable. So we have seen this already. Now, so I'm just going to write down the solution. Look, here we have theta is a random variable. Theta is a random variable that takes value uniformly. So it's a uniform random variable. With parameters 0 to 1. And this is our electrical signal, sinusoidal signal that you see. We deal with this signal. Y equals A cosine omega t theta, but theta is now random. Where A omega t are constants, A omega t are constant at a particular time instant we are talking about. And theta is a uniform random variable in the interval 0 to 1. The random variable y, so this is basically now y is a function of another random variable. Results from sampling the amplitude of a sinusoid with random phase. That find the PDF of random variable. Guys, PDF, what is PDF of random variable? We have uniform, theta is an uniform random variable. And we know the interval already. So uniform random variable solution. Theta is an uniform random variable. Actually, this is very similar to the previous example. I'm just going to write down the formula here. So, this theta PDF is f theta. Theta is basically 1 over b minus a, right? 1 over b minus a is your PDF. So b is your 2 pi. 2 pi minus 0 is going to be 2 pi. For 0 less than or equals theta less than or equals 2 pi, and it is 0 otherwise. So this is the solution of the first part. And the second part, find the expected value of y. So expected value of y equals expectation of g of theta, which is basically integration negative infinity to positive infinity g of theta and then f theta d theta. Now everything else is 0 except between 0 to 2 pi. So you just substitute these values and you have integration from 0 to 2 pi. G of theta is your a cosine omega t plus theta, and you have 1 over 2 pi. That's it. expectation is going to give you, okay guys, a over 2 pi. Can you tell me 0 to 2 pi? What is this integration? Cosine omega t plus theta. It's a sinusoidal signal. You are just adding a sinusoidal signal. What is basically the average, guys? It's very simple concept. From here to here, what is the average signal, guys?
0.
0. So this integration is going to give you 0. This integration is going to give you 0. You can do the calculation. It is going to be 0. So expectation of your signal is going to be 0. So this is the final answer. And energy of the signal is basically signal energy, signal power. You get the second moment of y squared, which is basically integration 0 to 2 pi. Because I'm writing 0 to 2 pi because everything else is 0. 0 to 2 pi y squared, and then f theta d theta. And this is basically 1 over 2 pi. So you substitute the expression of y. So integration 0 to 2 pi, it's a squared cosine squared omega t plus theta, and you bring 1 over 2 pi here, and you bring a squared out of the integration as well. So guys, do you recall that what is cosine squared theta? This trigonometric identity. So you can just write half times 2 cosine squared theta, and you can bring this half out, and it's basically 2 cosine squared theta equals 1 minus cosine theta. One plus section. Do you recall, guys? 2 cosine squared theta equals 1 plus cosine 2 theta. I'm writing this result directly, but just to show you that cosine 2 theta equals cosine theta plus theta equals cosine theta minus sine theta. So which is cosine squared theta minus sine squared theta, and cosine squared theta minus sine squared theta 1 minus cosine squared theta, which is basically two cosine squared theta minus 1. So your cosine 2 theta equals 2 cosine squared theta minus 1. So therefore 2 cosine squared theta is basically 1 plus cosine 2 theta. And that's exactly what we wrote. So this is from trigonometry identity, guys. This is not part of the solution. So you can just bring half here, and you can bring 2, and then you can write 1 plus cosine 2 of this quantity d theta, and then I am going to directly write down the answer. it is going to be A squared. So signal power E of y squared equals this A squared. So that's the final answer. Okay. Yeah, author also skipped many steps, but this trigonometric identity, you should know this from Calc 1. But if you just practice a little bit, you guys will recall these formulas. All right, so we have this example done. And in case you have a random variable that is a function of the summation, that is basically the summation of functions of of other random variable. So basically what I'm trying to say, y equals g1x plus g2x plus dotted plus g sub n x. If that is the case, how do you get the expectation? So the expectation of y is expectation of this quantity, and this expectation basically operator, we can remove it using integration, negative infinity to positive infinity, and you have this quantity, and then you have to add PDF using the formula, as per the formula. Now, you can bring this summation out of this integration. So you can bring this summation out of the integration to the integration negative infinity to x, and you have this quantity, and then you have PDF. Now, this is nothing but expectation of the function of expectation of individual function. So expectation of a random variable that is summation of other functions is same as the summation of expectation of individual functions. That's what it means. And I have one example, small example, and I gave you the solution. If y equals a naught, and there is a direct consequence of this formula, guys. So in the exam, I'm not going to give you this formula, this sort of problem, but you will be making use of this formula to solve numerical problem. So there will be direct use of this formula. So you have this is one function, g1 of x. This is g2 of x. This is g3 of x. Okay. So expectation of summation of these functions is going to be expectation is the summation of expectation of individual functions. You just pass this expectation operator. So you have basically nth more. So let's go through one example. So we have variance of x. It's the same formula, I just reiterated it. We went through this, and nth moment. Nth moment, we went through nth moment of random variable for discrete random variable. But here for continuous random variable, it is basically integration instead of summation. All of the expressions remain the same. What I am trying to do, so again, this variance of a Gaussian random variable, I proved it here. Eventually, you see that variance of x is sigma squared. But what I am trying to show you here, before I go through the example, for discrete random variable, guys, do you remember I had a summary slide? I had a summary slide for discrete random variable. For continuous random variable, I had this summary slide. So this summary slide will be really helpful for your exam. So make sure you can bring these formulas directly in your formula sheet. This summary sheet will will help you. So for uniform random variable, this is the range, this is the PDF, and then you have cumulative distribution function is this, and then mean is a plus b over 2, variance b minus a squared over 12. For exponential random variable, range is this much. Range is 0 to infinity, and then probability density function is for exponential distribution is lambda e to the negative lambda x, and then you have cumulative distribution function f sub x is 1 0 1 minus e to the negative lambda x, and then you have mean and variance. And this exponential distribution function has a memoryless property. This is another important property that people use in queuing theory and for estimation purposes for estimation of signal response. So here, what memoryless property says is that if x follows an exponential distribution, then probability that x takes value t plus h, which means that the next step, signal at next time step, next time instant. It is t is the current time, h is the t plus h, next time instant. Given that x greater than t is going to be all it depends, this probability, regardless of t, doesn't matter, like you keep estimating signal from, I don't know, from ancient time, and then you come up to the current time t, and then to estimate the signal at the next time instant, you just need to rely on the previous time instant, that's all. You simply do not care how you got there. And that's basically the fundamental property of Markov chain. That is another the topic of another course that will not go through, but that topic actually starts from this memoryless property. That when you estimate a signal, okay, estimating a signal at next time instant depends only on the previous time instant, and we simply don't care how we got to the previous time instant. Okay, so probability that x takes value greater than t plus h, given that x greater than t, okay, it depends on just the, this is your t, this is your t plus h, it depends on what is happening here in this time instant, in this time interval h. That's all it means. You simply forget what you did here. You simply don't care how you got here. So to estimate the signal, to find the probability of certain event at t plus 1, t plus h depends only on the previous time interval h. That's all. That's all this memoryless property is about. For Gaussian distribution, we have the range negative infinity to positive infinity, and we have the PDF, cumulative distribution function, mean and variance. Okay. So this topic requires little more careful attention because there are some examples that I will go through. So functions of random variables. Okay. So we will actually go through this topic in our next class. So we'll spend about half of the class next Friday to finish this chapter, and then we'll start chapter 5. Okay. So I would like to conclude this lecture here. Or you want me to continue? I can continue actually. cannot continue because this requires, now that's a long period, I'll be able to cover.